Hello guys, welcome to lesson 4. Before we start on the main focus of our lesson, I would first like to go over some of the things we have covered so far. So, covalent bonds are a shared pair of electrons between two non-metal atoms. So our negatively charged electrons, shown in red, are electrostatically attracted to the positive nuclei of atoms. Now that electrostatic word, all that means is the attraction between something that is positively charged and something that is negatively charged. So we can see here in this diagram, these positive nuclei filled with protons are attracted to the negative electrons of both its own atom and the atom that's sharing with. So remember, covalent bonds are shared pairs of electrons, and covalent bonds only form between non-metal atoms. In lesson 3, we had a look at covalent networks and covalent molecules. Now, covalent molecules have covalent bonds within the bond only, and they are connected molecule to molecule by very weak intermolecular forces. Covalent networks, on the other hand, they have covalent bonds between all of the atoms in the structure. Very, very strong bonds, very difficult to break those apart. Now we've also talked a little bit about ionic bonding. Now when metal and non-metal atoms react, they either lose or gain electrons to form ions. Now they do this to achieve a full outer energy level like their nearest noble gas. So metals will lose electrons to form positive ions, and non-metals will gain electrons to form negative ions. Now these opposite charges, this positive ion, this negative ion, they are very strongly attracted to each other, and they start to surround each other in one of these 3D lattice structures. Now they're either called ionic lattices, or sometimes they will be called crystals. Our official definition for an ionic bond is the electrostatic force of attraction between positive and negative ions. And it's important to note that ionic bonds are strong bonds. So the last type of bonding I want to talk about before we move on to today's lesson is metallic bonding. Now you don't have to worry too much about this. All you need to know is that it exists for holding atoms together in metal elements, and you need to know the definition, which is that it's a regular array of positively charged ions in a sea of delocalized electrons. Now what happens when metal atoms become bonded to each other in a metal element is that all of the atoms lose their outer electrons. So those outer electrons that are preventing them from looking like their nearest noble gas, they lose them. They give them up, and all of these electrons that have been given up by all of the atoms form this sea of delocalized electrons. There's thousands of them. They're delocalized, which means they don't belong to any of these now positive ions. So they don't belong to any of these ions here. They bounce from ion to ion. This negative charge attracted to this positive charge, then this positive charge, and that one, and that one, and that one. So the electrons, which are negatively charged, are free to move through the structure. So let's do that again. So metallic bonding is responsible for holding atoms together in metal elements. In metals, their atoms will lose their outer electrons to become positive ions. The outer electrons, which have been lost, are now free to move through the structure. And that structure can be described as a metal lattice. Now the ions are held together due to the strong attraction between ions and those electrons. So the attraction, even though the electrons are moving between electrons and ions, is holding the metal element together. Your definition for a metallic bond is a regular array of positively charged ions in a sea of delocalized electrons. And once again, your metallic bonds are very, very strong. If you need to pause here and either read through this slide or listen to me reading through or talking you through it again, please feel free to do so. And then press play again and we will move on to today's topic. Now, as I said, today we are going to be looking at the properties of substances. At the end of the lesson, you should be able to describe the properties of substances. You should be able to say that substances have different properties. You should be able to describe the properties of substances based on the different bonding. So, ionic bonding, what is the melting and boiling point like? What is the solubility like? What is the electroconductivity like? And we can relate these properties back to the type of bonding. Now today we are going to be looking in particular at melting and boiling points of substances. But before we go on to that, we are going to do a quick review of states of matter. Now, substances have different properties related to the bonding. So all the properties that we are going to look at, we can relate to their bonding. So we can say this substance has a higher low melting point because of the type of bonding involved. And when we talk about properties, we are referring to melting and boiling points, conductivity of electricity, and solubility. Like I said, today we are going to be focusing only on melting and boiling points. Now, sorry guys, there are three states of matter, and they are solid, liquid, and gas. This is something I am sure you are all familiar with. Now, melting is when a substance changes from a solid to a liquid, and boiling or evaporating is when a substance changes from liquid to gas. The reverse of these processes, from gas to liquid, is called condensing, and from liquid to solid is called freezing. Now, on the screen in front of me, we can see solid, liquid, and gas. In a solid structure, the atoms or the ions are tightly packed together. They are all touching one another. There's hardly any space between the atoms. In fact, there's no space at all. They're very, very closely packed together. At the I'm going to just put those on the screen for you just now. At the melting point, I'm going to go down here. At our melting point, a solid becomes a liquid. Now in a liquid, the particles are still quite close together, but they are spread out. There's space between the particles that make up your substance, and there is room for them to move. Whereas in a solid, tightly packed, no spaces between them. Now when we go from a liquid to a gas, at the boiling point, the space between the particles becomes much, much wider. In a gas, the particles are very, very spread out. Now, to bring your attention back to the top here, solids melt to form liquids, they boil to form gases. If we want to go back from a gas to a liquid, we cool everything down and it condenses into a liquid. We can go even further by cooling that liquid so that it freezes and becomes a solid once more. If you imagine you take some ice cubes out of the fridge and you were to leave them sitting out, perhaps in a glass, they would very quickly melt. If you were then to take that water and pop it in the kettle or put it in a pan, or a pot rather, on your cooker. Had to think about that for a second. You could heat that water up and it would boil and form a gas. Now, when you boil a kettle, sometimes you will see condensation on the wall behind it, maybe there's a window behind it and you can see the water that comes out and condenses on the window. Now inside the kettle the water was boiling hot, becomes gaseous water or gas water, and then it hits the air outside and it starts to cool down immediately. When it starts to cool down, it condenses back to liquid, and you can perhaps see that on your walls, on your windows, around the kettle. If you were to collect that water, if you were super dedicated, collect the condensation and popped it in the freezer. When you went back to check on it a little later, you would find that it had frozen and returned to being a solid. So solids become liquids at their melting point, liquids become gases at the boiling point. So we are going to use that information to work out physical states. So a question that you might be asked is whether a substance is a solid, liquid or gas at room temperature. Now your data book has information on the melting and boiling points of elements on page 5, and it has the melting and boiling points of selected compounds on page 9. So when we do this activity, you're going to use your data book to find melting and boiling points. Now, when we're asked about room temperature, always just take room temperature to be 25 degrees centigrade. And where 25 degrees comes in compared to melting and boiling points of a substance will tell you the state the substance is in at room temperature. I'm not going to just leave you to do a wee activity on your own. I'm going to talk you through exactly what you have to do. So, before we move on, pause the video, make sure you've got your data booklet, get it open to page 5. And remember that room temperature is 25 degrees C. I need those data booklets open. So, solid, liquid, gas. As the temperature increases, you will reach your melting point and your solid will become a liquid. As it increases even more, you will reach the boiling point and your liquid will become a gas. You might be asked, what state is sodium at room temperature? And the first thing you've got to do is find sodium's melting point and boiling point, and then work out where 25 degrees C comes in. So, its melting point is 98 degrees centigrade. Its boiling point is 883 degrees centigrade. And 25 degrees room temperature is well below 98, which means that sodium would be solid at room temperature. Let's do another one. So, let's think about argon. Argon has a boiling point of minus 186 degrees centigrade and a melting point of a chilly minus 189 degrees centigrade. So where do you think 25 degrees comes in? Is it going to be below minus 189, between minus 189 and minus 186, or is it going to be above minus 186? Well, if you guessed above, you were quite right. So argon, then, is a gas at room temperature. Let's have a look at mercury. Mercury is one of the transition metals. It's a very special transition metal, and you're about to see why. So, melting point of minus 39. So at minus 39 degrees, solid mercury becomes liquid mercury. At a toasty 357 degrees C, liquid mercury will boil to become a gas. So where does 25 degrees fit in? Well, it fits in, thank you slideshow, slap bang in the middle. It fits somewhere in between minus 39 and 357. And that means that mercury is a liquid at room temperature. So, here is what you have to do just now. Now, this table is included in an assignment in your assignment tab. You're going to pause the video here. You are going to get your data booklet. You should already have it in front of you. You're going to get your you're going to get your data booklet and you are going to work out the melting and boiling points of all of these substances, from magnesium all the way down to methane. You are going to use the melting and boiling points to work out the state at room temperature. And while you do that, let's have a look to see if you can see any patterns in the states at room temperature for metals, for covalent networks, for covalent molecules, for ionic substances. And have a look at the melting and boiling points. Are there any patterns there depending upon the type of bonding present? So let's get the video paused here, go and do your assignment, and then come back and we will restart the video. Okay, welcome back. So, here is what we should have seen from completing that table. Now, our metallic elements, they have a range of melting and boiling points. They can be kind of middling to quite high, and they are all solids at room temperature with the exception of mercury. So metals have a range of melting and boiling points. Some are quite low, some are quite high, but they are all solids except mercury. Now, covalent molecular structures, they also have a range of melting and boiling points, but they are usually quite low. They can be solids, liquids, or gases at room temperature. They don't prefer one of the three. It depends on where the boiling points are. Covalent networks, on the other hand, have very high melting and boiling points. They are all solids at room temperature. Ionic bonds have high melting and boiling points, and they are solids at room temperature. That is the summary of what you viewed in that table you completed. So, I'm going to say it one more time. I'm going to go back, we're going to say it again. Covalent network, very high melting point and boiling point, all solids at room temperature. Ionic substances also have high melting and boiling points, and they are all solids at room temperature too. Covalent molecular usually have quite low melting and boiling points, so they tend to be liquids or gases at room temperature with a very few exceptions, sulfur being one of them. Sulfur is a solid at room temperature. So covalent molecular, a range, solids, liquid or gases at room temperature, but they do tend to be liquids or gases. Metal compounds, or metal elements, have a range of melting and boiling points, so again, they vary, but they are all solids at room temperature with the exception of mercury. So I hope you've still got that data booklet out, because here is your next task. So you are going to, hopefully you'll have coloured pencils to your disposal. If not, coloured pens work fine. You are going to find lithium, sodium, potassium, beryllium, magnesium, calcium, and aluminium on your periodic table, and you are going to pick a colour and shade these in. Somewhere on your periodic table you're going to add a key, and you are going to indicate that these elements shaded in that particular colour are metallic lattices. You are then going to do the same for your covalent network elements. Now, your covalent network elements are carbon, boron and silicon. So pick a second colour, colour those in and add that to your key. You are then going to pick out your covalent molecular diatomic gases. They are hydrogen, nitrogen, oxygen, fluorine and chlorine. Now you will note that bromine and iodine are not on this list. Bromine is in fact a liquid and iodine is a solid at room temperature. Your covalent molecular solids are phosphorus and sulfur. Iodine should be on that list, but just colour in phosphorus and sulfur for the moment. And your monatomic gases, helium, neon, argon are also called noble gases. So that word monatomic, in case you do not know, means single atom. So helium, neon, argon, they don't form bonds to anything else. They exist as single atoms. So pause the video, colour it in, sort your key, and then we will be ready to begin and pick back up once more. So, we're getting to the end of the lesson now. What I want to draw your attention to is state symbols. So, state symbols in chemical equations, they will tell you the state that your reactants and your products are in. Now, state symbols, obviously we know, substances will either be solids, liquids or gases. They can also be in solution, which means they are dissolved. Now, in chemistry there's a code to describe the physical state of a substance because it would take far too long for you to write in a chemical equation solid magnesium, gaseous oxygen, a solution of sodium chloride. That would take far too long. So instead we have a code, we have state symbols which will help you write this shorthand. Now, what I would like you to do, now this isn't in the notes that I gave out, at least I do not believe it is in the notes that I gave out. So take your jotter, if you don't already have this written down somewhere, you are going to write down this note. So substance exists as solids, liquids or gases. They can also be in solution, which means dissolved. And we use a code of state symbols to describe the physical state of a substance. And that code is as follows. A lowercase s in brackets is for solid, L in brackets for liquid, G is for gas, and AQ is for solution. So if you've not got that written down somewhere already, whip your jotter out or a piece of paper out that you're going to keep with your notes and write this down. It will be important later on. So I am going to stop there for today. What you are going to do now is you are going to complete pages 8 and 9 of your workbook. If you do not have a physical copy, if you weren't able to get into school to get that, you can find it in the files section under bonding and properties online. Should be in that folder. If you can't find it, let me know. I'll send you a copy, but I should know already if you don't have a copy because we're 4 lessons in. It's a bit late to not have a copy of it, but that's okay. I'll overlook it just this once. So, you're going to fill in pages 8 and 9 and you are going to make sure that you've taken part in this week's chemistry challenge, that you have completed all of the assignments for this week and that you are happy with the material that we've covered. If you have any questions, let me know and I will speak to you all very soon. Bye guys.